Welcome back, students. Today we are going to continue again our discussion on exercise problems of chapter number 12. And today we will take to 52. And of course, some questions which are not relevant, we will leave them. So we are discussing at the end in the last lecture that how to determine the units. How to determine units of ZX and RX. And ZX, RX are a collection of polynomials. That's ZX. This is a notation for this is a collection of polynomials. Polynomials with integer coefficients. Integer coefficients. That is, this is a collection of polynomials like Px equals to, for example, if we can write Pn x to the power n plus Pn minus 1 x to the power n minus 1 dot and plus at last there would be some constant, okay, like this, where pi's are member of the integers, okay. And this is in case of 25th, okay. And in 26th question, they are considering Rx, that is polynomials with real coefficients. So between these two, only the difference is that here the coefficient. In this case, the coefficient, these P1, P2, and this Pn, they will be real. And in the question number 25th, they will be integer. Okay. So of course, the ZX is going to be the superset of, no, this is a RAX is going to be the superset of ZX. Okay, at least. So to determine the unit, I mean to say that we need to find the elements in ZX which are having inverse. Okay, which are having inverse. So we need to find the collection in 25th question. We need to find the collection of fx. These are the polynomials in ZX. How should be they? Such that there exist gx, so that because the identity element here, multiplicative identity in ZX is 1. So we need to find those fx for which there exists a gx such that their product is going to be 1. Okay. And this gx also should be a polynomial with integer coefficient. This integer is going to be a polynomial with integer coefficient. For example, if you are taking, suppose fx equals to, you are taking x square plus x plus 1. Okay, this is a polynomial. Then if you are taking another polynomial gx like this one of fx, so this is going to be x square plus x plus 1, and provided that the denominator is non-zero. So the coefficient of this one is not going to be an integer, you know. If you expand this 1 plus x square and then inverse, then in that case you may not always get what is called the integers, you know, because factorial kind of thing may be coming here also. Okay, factorial kind of thing. And then by 2, by 3, by 4, something like this, it will be coming here. Okay, if you expand this kind of thing. Okay, so they are talking about all in general, all polynomials, not in particular case. They are talking about all those polynomials. And this polynomial is nothing but we need to have fx inverse like this identity. And for this, we have only two possibilities. Okay, when the product of these two is 1. So either they are exactly 1 or they are -1. Okay, so the collection will be either 1 or -1. These are the polynomials, and you know that one can be written as x to 1 times x 1 into x to the power 0, and -1 can be written as -1 x to the power 0, like this. Okay. And in case of similarly, in case of 26th question, we need to find out the polynomial such that their product is going to be 1. Okay, their product is going to be 1, and okay, it's going to be 1. And in such cases, what we need, okay, we need to have fx equals to constant. Okay, so if we are taking any constant here, it was constant, but not only 1 and -1. And here in this case, this is a constant and should not be 0. So that fx, and when you are taking this fx, so they are going to give you 1 when they are cancelled out. Okay, when their values are non-zero. So this collection comes out to be fx such that fx equals to c. And more we will see in the degree when we will discuss the degree of a polynomial later on. Okay. So actually this requires something more for better explanation. But anyway, by that time you can understand at least these things. And 27th question is that show that a unit of a ring divides every element of a ring. So we need to take some unit. 27th question. Okay. So let A be a unit. We are not writing the unit because a unit may be so many. Units may be so many in a ring. Okay. So then we can write B equals to, so if A is unit, it means that A inverse exists. Okay. So we can write B as A and A times A inverse times B, and then we can bracket it out. Okay. So then this implies that you see this B is a product of A and A inverse B. So it means what? That this A divides B. Okay. This implies that A divides B, and for this is true for any B belongs to the ring. 28th question, it says that in Z6, so that in Z6 4 divides 2. Okay. In Z8 3 divides 7. And here in Z15 9 divides 15. So how you can show? You can show them in based on this the above 27th result. Okay, result number 27. You can show. So what you need to show? You need to show that you need to find an element which is a unit, and then it will divide every element of the ring. Okay. So what are the units here in Z6? In Z6 we need to prove what? 4 is unit. Okay. So that 4 divides 2. Very interesting. 4 divides 2. So in Z6 we can write okay. In Z6, what is the inverse of Z4 in Z6? So that this becomes identity, that is 1. So what should be the value of 1? X? Do you have any idea? Hello?
3.
3. Okay. So 4 times 3 equals to 12, and 12 is divided by 6. This is going to be 0. Okay. Okay. Now we need what? We need inverse now, not 3.
Okay, sir. Sorry.
How come it with 3? You find out. And similarly, here also you can show that 3 is unit. Here in Z15, you can show that 9 is unit. And then accordingly, you can, okay, accordingly you can find out. Okay, fine. So of course, 4 times 1, 4 times 2 is 8. Okay, 4 times 3 is 12, 4 times 4 is 16, 4 times 5, 20, 20 divided by, okay, okay, I think we may be missing something, but you need to show this,
सर
this
नहीं
is
आ रहा है
unit,
वो
that's
आंसर।
why. It is not coming. Hello. Hello.
यस सर।
4 is not unit or what? Hello. Hello. Are you trying or what? Okay, you can see here in Z8. What about 3?
सर 3 तो 0 आ रहा है सर, उसके बाद 0 to 5 में नहीं आ रहा है सर एलिमेंट जो 1 दे।
Yeah, because we want to show that a unit of a ring divides every element of the ring. This may be, I don't know whether they have written or there is some typos. This should be. What about in Z15? Or we can write like this. If it is not so, then this is a way of doing the thing, but we can still try. They are telling that 4 divides 2, na? It means that there exists some integer, some number such that 2 equals to 4 times something, na? Okay, so 4 times 2 equals to 2, I think. Na? If you divide it by 6, then we are getting this is equals to 2. So this way, I don't know. Okay, so I think this is not applicable on this. No? You can say, you can try this one. If this is unit, okay, then certainly this is going to divide every element B of the ring. But if it is not unit, then we cannot say that it is not, it may not divide or it is not dividing. Okay. So here you see that we can write it 2 as 4 times 2. It means what? 4 divides 2, na? And similarly in Z15, we can write 3 times 7. It will be, no, 3 times 5, I think. Yeah, 3 times 5. 3 times 5, this is 15, and 15 when divided by 8, this is going to give us 7. Na? Remainder is 7. Hello. All right. This is first part. This is second part. So this shows that 3 divides 7. And then
सर वो Z8 में शो करना है सर, Z8 में यूनिटी आ रहा है सर 3।
then in case of unity, if 3 is the 3 is unit, 3 is unit, you mean
यस
to
सर,
say, na?
3 times 3।
Yeah, then in both way you can say if 3 is unit, 3 and you can find x such that this is unity. So what is the possibility for x?
3 self inverse।
3 itself, na? 3 inverse, okay. 3 to the power, 3 to the power 2. It means 3 square, this is going to be identity. Okay, this is self inverse. So 3 not only going to divide only 7, but it will divide every element of Z8. Okay. But here, because 4 is not unit, so at least we can say this. What other element we can try it out. In Z15, we need to show that 9 divides 12. Whether first question is if it is unit, then all right. Otherwise, we will try some more way. So what about 9 here? I think 9 times 3. This is going to be 27. 27 divided by 15. This is going to be 12. Na?
12.
and rest you can verify whether it is unit or not. Okay, so you got
यूनिट
or
नहीं है
what? यूनिट नहीं है ना, बढ़िया, ठीक है. So अगर यूनिट नहीं है, then we can say at most this one. Okay, if it is unit, that we can not only say this, but we can say that 3 should divide z 1 2 3 4 5 6 7, all right, every element of z8 including 0, of course. So in 29th question, suppose that AB belongs to a commutative ring R with unity. So this we need to take care. We need to, when you are reading some question, then you need to highlight the what called the adjectives they are using or the property they are having. So commutative and with the unity, two things. If A is unit, again they are using that A is unit of R, then and B square is 0, then we need to show that A plus B is unit. So this is giving another criteria without actually showing that some element is unit. We can find out that we can claim that that particular element is going to be unit. Okay. Okay. So for that, we need to have this element should be unit, and this element, square of this element, is going to be 0. Okay. Okay. So we need to show that A, B is unit, A plus B is unit. 29th question. So let us for this to show this is unit. It means we need to find some element which product with A plus B is going to be your identity. Okay, so we can write A plus B, and because A is unit, so A inverse exists, and then we can write A inverse exists. So A inverse to the power 2 is going to be A to the power negative 2 times B. Okay, and then we multiply them. So we will be getting 1 minus, okay, 1 minus uh, 1 minus A inverse B plus B, A inverse, and minus A to the power minus 2 B square. Okay, and because it is commutative, okay, because it is commutative, so these two will get cancelled. Okay, so we are left with 1 minus A to the power negative 2 and B square. So because B square is 0, so we are left with 1. So A plus B, its inverse is going to be A inverse minus A square, A to the power minus 2B, like this. Fine. So let us see the question number 30th. We need to do quick. Okay. Question number 30th. What it says that suppose there is an integer. Such that all elements for a positive for some, so that A is 0. Okay. Hello.
सर वो कैसे
Hello.
मल्टीप्लाई किए सर, मतलब वो उसका ट्रिक क्या है सर कि इनवर्स वो पहले आइडेंटिटी आ जाएगा सर मल्टीप्लाई करने से?
To find out this one, either you can take some element here x, and then you can go in reverse way to solve for this. Are you getting?
Yes sir.
Yeah, in reverse way you can get. Otherwise, because A plus B is there, so what we used to have in set of integers or real numbers. So from there we can get some idea. Otherwise, this is only a thing. Actually, these questions are made if they are coming in the proof of some problem, some big problem. So from there they used to take. Okay, this is they are using. So if it is happened, so A plus B is going to be unit. That's all. So this is found in that at that place in some proof. Suppose I'm proving some big result, and there we can from there in the proof we can get so many small result. So that's what they are using. Otherwise, you can go reverse way. Okay, so you can put some x, then you can try to solve or guess. Fine. Okay. Next, you can try the 30th question yourself. Okay, if you are not able to do, then let me know. I'll tell you. Question number 31st, give an example of a ring of element with elements A, B with the properties that A, B equals to 0, but B is not 0. You can get them in matrices, I guess. Okay, so you can keep a first row 0, first column 0, and then here you can write out. You can keep any element here. Maybe you can write 100 or 10, something like this. Okay, and then suppose this is A. Okay, and then you can take B where one row is 0. Okay, in one column is 0. Here first column is 0. Okay, then you need to make here the second row should be 0. You can take like this. Okay, fine. So you can take the product 8b times 0 and then ba times is not 0. Okay, b times a is non-zero. This is question number 31. 32. Let n be an integer greater than 1 in a ring in which x to the power n equals to x for all x. Okay, so that a b equals to 0 implies b equals to 0. So here in general they are giving some example here in this case that AB, if AB is 0, it is not necessary, then B is 0. But in the question number 32, they are telling that under what condition AB equals to 0 implies B equals to 0. You see, when AB equals to 0 implies B equals to 0. All right, both product. So for that, this should hold. This is sufficient condition for this. Okay. So here n is greater than 0 is any integer. All right. And x to the power n equals to x for all x belongs to that particular ring. Fine. So it is giving that AB equals to 0. Fine. So let us consider BA. So BA we can write BA because okay, let us write A and B belongs to the ring, and so therefore their product is also going to be belongs to the ring. So this implies that AB also belongs to the ring. AB also belongs to it. So ABA equals to BA to the power n, and this is a by assumption of the result. Okay, by supposition. So we can write it as a BA and then again BA and then BA to the power n minus 2. And we can write this BAB, okay, and then A, then BA n minus 2. Fine. So you see this is 0. So if it is 0, then this is going to be 0. Fine. So this proves the result. And next question number 33. Suppose that R is a ring such that x cube equals to x for all x in, then prove that 6x equals to 0 for all x in. Okay, so this is question number 33. We have been given x belongs to R and x cube equals to x for all x belongs to the set of that is ring. Okay, this is a ring, and then we need to prove that 6x. So for that, because this holds for every x in here, so therefore we can write 2x equals to 2x cube, and this is equals to 8x. Okay, and this implies that 8x equals to 2x, and this implies that 8x minus 2x equals to 0, and so 6x equals to 0. Question number 34. If A belongs to a ring, e to the power 4 equals to 2, then we need to prove. Okay, you can use induction here. We can use induction for n equals to 1. Okay, a to the power 2 times 1 equals to a 2 but a, okay, this is equals to a square, okay, and this is true, you know, this is true, okay, for n equals to 1 is true. So let this is true for n equals to k also, okay. So this means that a to the power 2 times k, this is equals to a square. And now we can multiply on both sides a by a square, a to the power 2k equals to a to the power 2 times a to the power 2. Okay, this implies that in the left side we can take 2 common, we can write k plus 1, a to the power k plus 1, and this is equals to a to the power 4, 2 plus 2, okay. And a to the power 4 is nothing but we have been given equals to 2. So this is a to the power 2. Okay. So this proves that this result is also true for n equals to k plus 1. 35th question, for any integer n is greater than 1 such that a to the power n is a for all a belongs to Z6 to the same for Z10. Okay. So this question, they are telling that a to the power n equals 4 in Z6, and this kind of result I think we have seen here something similar result where it was maybe here I think, okay, in question number 30th. Suppose there is an integer x to the power n for all, so then okay, this 30th question and this question they are, I think they are similar, but this is a particular case. Okay, for some integer, okay, in Z6 they are talking about, in Z6 we can take of course this you need to try it out, okay, but for n equals to 3 this will hold, for n equals to 3 a to the power 3 equals to a for all a belongs to Z6, okay. And for Z10 you can take n equals to 5 and verify this, okay, this you can verify when a belongs to Z10, okay. I'm not sure about this, but I'm guessing, okay. Hello, so that you can verify it, huh? And in the rest part you can take m equals to, they are telling that so that no such n exists for z to the power m when m is divisible by square of some prime. So m is divisible by square of some prime. So this could be of this form p square t. Okay. So certainly because p is a prime, So therefore this m and m is divisible by this. Okay, m is divisible by this, and therefore m should sorry. I mean to say that pt to the power m is divisible by square of the prime. Okay, so therefore m will also be divisible by this pt. Okay, m is will also be divisible by pt because p is prime. M divides pt. Okay, m divides pt because p is prime. Okay, so p to the power, when it divides, it means what? The remainder is going to be 0. Yeah, and this holds in Zm. Okay, in Zm as p divides, sorry, m divides pt. M divides pt. You can write a better explanation for this. Okay, m. All right, you can write down. In 36, question number 36, mn be positive integers and k be least common multiple of mn such that. that M and M intersection NZ is equals to KZ. So this is nothing but intersection of subring kind of thing. Okay. 36 question. So if Mn positive integer, K least common multiple. Okay. So we can write K equals to Ms and K equals to Ms and K equals to Nt, because K is least positive multiple, least common multiple of M and N. Okay. For some S and T belongs to the set of integers. Okay. And therefore we can write what? We can write Ka as M times K is Ms, and then A Ms and A, and this is equals to M times Sa. M times Sa. Okay. So this is a number of the form M times something. Okay. And similarly, you can write K as Nt times A, and this is going to be Nt times A. Fine. So you can express every Ka in this form and in this form as well. So it is M times something, it is N times something. It means what? This implies that Ka belongs to Mz intersection Nz. Okay. So like this. And this means that this proves one way of inclusion. One way of inclusion. For other way, suppose we can suppose that suppose B belongs to Mz intersection Nz. So it means that B is going to belongs to B will be common multiple of M and N both. No? So B belongs to KZ kind of thing. Okay, where K is the least common multiple of these M and N. Question number 37. Explain why every subgroup Zn under addition is also a subring of Zn. Do you have any simple question? Why subgroups of Zn under addition is also subring? So reason is that the subgroups of Zn is closed under multiplication. Okay, is closed under multiplication. And of course, because it is subgroup, so additive inverse will be there. So difference will be automatically there. What thing is missing? Closeness of under multiplication was missing. Okay. Question number 38. Quick answer, please. Is Z6 is a subring of Z12? Hello. Yes or no? No, because they have different part operations. Na? In Z6 we use multiplication modulo 6 here, or yeah, multiplication modulo 6 and addition modulo 6 here also. But here we use multiplication and addition modulo 12. So for that, for a subring, it should be a first subset. Okay, and subset they contain the same number, same type of elements, and operations also they should be there should be same operation on both. In 39th question, quick reply. Any can you do this? S is constructed like this. R belongs to capital R. So we need to prove that R is a subring. Of course, there is a criteria. So we need to prove A minus B belongs to S, and the product of two element of S is also in S, that is closeness. Okay. So we can take A R1A minus A R2A, and this equals to, we can take common A R1 minus R2A. Okay. So because S is a ring, this R is a ring, so R minus R2 is also going to be in R. So this will belongs to S. All right. And about the product A R1A times A R2A, and this is equals to A square R1 R2A. Okay. And because R1 R2 members of R, and therefore they are A, this is going to be, this is A square, I think, yeah, A square, okay. So we have, this is R3 and A square. And moreover, A square is nothing but what is given, A square is 1, okay. A square is given to be 1. A square or I have done some mistake. I think, yeah, I did mistake, I think. This should not be like this. This is equals to A, and then A from left, and then R1, and then A square, R2, and A, like this. All right, something like this. Okay, so this is equals to A square is identity. So we are left with A R1, R2, A. So this belongs to S again, because R1, R2 belongs to R. And they are asking that does S contain 1? So we can write 1 as, if you take R1, then we can write it as A times 1A, and this is equal to A square, no, and this is equals to 1. Fine. Okay, so this is going to be a member of S. So yes, okay, yes, S contains 1. Question number 40, 41, 42. These are simple examples from 2x2 matrices, and you need to prove or disprove that they are subring. So do yourself. You can verify. Okay. Question number 43 we are not going to do because we have not discussed anything like direct product or something. Okay, so this is not part, so we will leave it. Question number 44, we can try it. Question number 44, it says that A square equals to A to the power n equals to A for all elements A of some ring. Okay, then we need to prove that A is equals to a negative A. Okay, so and moreover that n is a positive integer, so we can take let n equals to 2 times m, and because this is a positive integer, so m is going to be greater than or equals to 1. Fine. So minus a, we can write it like because for all elements this holds, so we can write minus a times minus a to the power n, and this is nothing but a minus a to the power 2 to the power, sorry, yeah, 2 to the power m, and this is equals to a to the power 2m, a to the power 2m, and a to the power 2m, but nothing but a to the power n, and this is equals to a. Here it is given. Okay, so what we have, minus a equals to a. Next question number 45. Let R be a ring with unity 1, then so that n times 1 is a subring. I think you can do this. No? You need to verify it. You need to verify it that n1 times 1 minus n2 times 1, and then you can take n1, you can write n1 minus n2 times 1. Okay. So this is a because difference of two integers is also is going to be an integer, so therefore this belongs to S. And similarly, you can take n1 times 1 and then n2 times 1. This is going to give you n1 times n2 and times 1. This also belongs to n because product of two integers is again an integer. Question number 46. In question number 46. Question number 46. 2u 2z union 3z. Okay, so you can take 2 plus 3. 2 belongs to their union and 3 belongs to their union, and their sum is equals to 5, and 5 is not a member of their union. 2z union 3z. Okay, so it is not closed even under addition, so this is not a subring. Okay, not subring. Question number 47, it says that determine the smallest, you need to find the smallest subring of Q that contains 12. So Q is the set of rational numbers. Okay, so we can take S as the set of integer, set of the numbers of the form m divided by 2 to the power n. You can take 2 to the power n. Okay, m belongs to the set of integer and n belongs to the set of positive integer. Okay, so this going to be this going to contain, this contains what, 1 by 2. Fine, you can take m equals to 1 and n equals to 1, so 1 by 2 will be there. And then they want that this should be what, that is subring up with property. Okay, 1 by 2, and this will be the smallest. Okay, so anything, because anything which contains the power of 1 by 2, that should contain this one. So for that, if you take t and this contains all powers of like this. Okay, all powers of m belongs to the set of integer, so this will supersede this set. Fine, so this is going to be the determine the smallest subring of Q that contains 1 by 2, that is finding subring S with the property S contains 1 by 2, and if T is any subring containing 1 by 2, then T contains S. Okay, so T should be T contains 1 by 2, then it should supersede this set. Okay. Just a minute. Okay. Yeah, because every power of a 1 by 2 to the power m, it will be there. Fine, because of closure property and subtraction also we can take. All right. 48th question is similar to that. You can take. You can do yourself. Question number 49. Question number 49. It is easy. You can write a plus b and a minus b. Okay, and then a square and then b plus b a minus what is called b square and plus is there or what, minus ab. Minus ab. Okay, for all if and only if it is commutative. Okay, so this yeah, this is commutative. Okay, this implies that because in the left hand side we have a square minus b square. If at all we want this one, then what should be there? If and only if ba minus ab equals to 0. ba minus ab equals to 0. Fine. And that is AB equals to BA. In next question, question number 50th, suppose R is a ring with A square equals to A. This type of ring where this hold for all elements, they call Boolean ring. Okay, Boolean ring they called. So that R is commutative. Okay, so for this you can take A plus B square, and this is A plus B square equals to A plus B. Okay, by this is given, and then this implies that A square plus AB plus BA plus B square plus B square. Okay, all right. So like this, and so okay, AB plus BA equals to 0. This implies that minus AB plus BA minus AB minus AB equals to BA. Suppose this is star, and also minus AB equals to, we can write minus AB whole square. Okay, AB whole square, and this implies that minus AB equals to AB square, and AB square nothing but AB. Okay, so this is star dash. So from these two, you see here minus AB is there, left side is equal. So this implies that BA equals to AB. Okay. Question number 51 we can leave, because Boolean ring I don't think there is anything we have in syllabus. Anyway, you can try if you want. Question number 52. Yeah, this kind of question we discussed in the last lecture. That A, B, C are elements of a ring. Does this equation always have a solution? So we can take. We took some, I think, example 2x equals to 2 or something we have taken. Nah? Something like this, or 2x equals to 1. No solution in Z4, and 2x equals to 0 has two solutions in Z4 in the same ring. Okay. Further, they are telling that if A inverse exists or A is unit. Okay. So if A is unit, it means then A inverse exists. And we can write therefore Ax equals to C minus B. Okay, and then x equals to C minus B, and we can multiply it by A inverse. Okay, so this is going to be solution. This is a unique solution. So with this, we have discussed almost every question of this exercise of chapter number 12. Okay.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.